My lady's story, my lady's story. My lady's story is one of annihilation. My lady's story is one of breast.
Section 1.4 is on adding and subtracting radical expressions. I think this is another section we worked on last year a little bit. So we're going to be looking at this, like radicals, but I thought what I'd do is I'd compare it to like terms. Remember, like terms is when we added and subtracted polynomials, binomials, monomials, trinomials, all that kind of stuff. And when you combine like terms, you have to have the same variable, or variables if there's more than one variable, and you need to have the same exponent, or exponents if you have more than one exponent. So, for example, if you were adding something like 6m plus 7m squared, if you were asked to combine those, can you do that? No, you have the same variable, m and m, but the exponents are different. This is a 2 and this one's a 1, so you can't add them. You just leave it like this. There's nothing to do. But if it was 6m squared plus 7m squared, then you could add them. They have the same variable, m and m, and the same exponents, 2 and 2. So if you have 6m squareds and you add another 7m squareds, you now have 13m squared. Okay, one other example. If it was 9n cubed n minus 18m cubed n, everything has to be the same. If this is m cubed, it has to be m cubed. If this is n to the first, it has to be n to the first. It has to be exactly the same. Okay, so we have 9 of these things, m cubed n. We're taking away 18 of these things, so we end up with negative 9 m cubed n. Okay, very similar to that is with radicals. You need to have the same index and the same radicand. Now, do you remember those? We've talked about this just a little while ago. If you had something like the cube root of 27, let's say, then the index is the small number here, and the radicand is the number out front. There can also be a coefficient out front here, right? A number you multiply it by is called the coefficient, and that could be any number you want. I'll put a 5 up there. That means 5 times the cube root of 27. Okay, so some examples of that would be like 5 times the square root of 3 plus 2 times the square root of 13. Can you do that? No, you have the same index. They both have an invisible 2 there because they're square roots, but you have different radicand, 3 and 13. So just like this case here, they're not like terms or they're not like radicals, so there's nothing you can do. What if it was 5 root 3 plus 9 root 3? Okay, now we do have the same index. They're both 2 and 2, and we have the same radicand, 3 and 3, so we can add them. 5 root 3 plus 9 root 3 is 14 root 3. And one more example, if it was 8 and then the fifth root of 8, and we're taking away 7 and the fifth root of 8. So this is 8 times the fifth root of 8 minus 7 times the fifth root of 8. So they both have the same index, 5. They both have the same radicand, 8. We can do this. 8 take away 7 is 1 times the fifth root of 8. That's just the same as the fifth root of 8. So we're done. Okay, the most important thing with this is that when you're adding, you need to have like terms, or you need to have like radicals, just like we talked about. But here's the thing I haven't mentioned explicitly yet. You get the same term or the same radicand and in the answer. So if you're adding 6m squared and 7m squared, you end with 13m squared. If you're adding 5 root 3s and 9 root 3, you get 14 root 3. It doesn't change, right? It doesn't become m to the fourth. It doesn't become root 6 or 9 or something like that. The radical stays exactly the same. Okay, let's do some examples. We have root 50 plus 3 root 2 here. And we said you can only add like radicals. These are not like radicals. They have different radicands. So, can we do this? Looks like no. But don't give up. What do you have to do before you give up? You have to put them in simplest form. You got to simplify these radicals. So let's make a tree. 50, well that's 5 and 10. And then 10 is 5 and 2. And since there's an index of 2, we're looking for a pair. And we do have a pair. The pair is right there. So what we have is 5 root 2. The 2's left inside. We couldn't pair it up. plus 3 root 2. We can't simplify that. And 5 root 2 plus 3 root 2 is 8 root 2. The radical stays the same. Root 2, root 2, root 2. Okay, simplify before you give up, because right now it looks like there's nothing you can do, but we're going to simplify. 27 is 9 and 3, and 9 is 3 and 3, and we're looking for a pair. And you do have a pair. You got a pair there. So this is negative. We'll leave the negative outside. 3 comes out, and this 3 stays inside. Plus, you can't simplify this radical. 5 is a prime number, so it just stays as 3 root 5. 80 you can certainly give a shot at. Let's do 8 and 10. 8 is 4 and 2, and 4 is 2 and 2, and 10 is 2 and 5. And we're looking for pairs, and you can get 2 pairs in there. So a 2 comes out, and another 2 comes out. 2 times 2 is 4. So we have take away 4, and a 5 remains inside. Take away 12. We have 3 and 4, and that gives 2 and 2, so you can make a pair there. So this 2 comes out, but there's already a 2 out there. So that means the 2 coming out and this 2 that's already there get multiplied together. So you end up with 4. And what's left inside is this 3. Okay, do we have any like radicals? Well, here we have a root 3, and here we have a root 3. So we have negative 3 root 3, take away another 4 root 3. That gets us down to negative 7 root 3. And then we have a plus 3 root 5, take away a 4 root 5. So positive 3 root 5, take away 4 root 5 is equal to negative 1 root 5, but I don't need to put the 1. So this would be our answer right here. Okay, we're looking for fourth root this time. So let's try just the 81 here. We got 9 and 9. 3, 3, 3, 3, and we're looking for a group of 4, and that's exactly what we have here, is a group of 4. So we know that we can get a 3 coming out. Now, let's look at the p's. You need 4 of them to come out. You only have 3 of them, so those can't come out. If you look at the q's, you have 5 of them. I'll just write them here. 1, 2, 3, 4, 5 q's, and you need a group of 4, so you have that with 1 left over. So I can write the 1 q, and then it's still the fourth root. We didn't do anything to the p's, and we had 1 q left over. Minus, okay, 2. P's, again, there's nothing you can do with the p's. Q's, oh, it's the same situation. You can take out 1 q, and you're going to be left with 1 q inside, and we have p3q like that. So we got 3q times the fourth root of p cubed q, take away 2q times the fourth root of p cubed q. So this is great. This is all like terms or like radicals. So 3 of them, take away 2 of them, will just leave you with 1 of them, which you don't even need to write. So you just end up with q, or 1q, times the fourth root of p cubed q. Wow. Also, they won't make you do this, but you should, I guess, worry about absolute values and that kind of stuff. It's rather complicated because in this case, your p's and q's could both be positive, or they could both be negative. But you couldn't have one being positive and one being negative. I'm not going to go into explanation for that because it takes too long, but that's the facts. But if you look at it, since a q came out, it's not possible for that letter, that number, I suppose, coming out to be a negative number because you're taking a fourth root. It's an even exponent. So if you really, really understand, this would be an absolute value. However, I know some of you are cursing and swearing. You're going to find that for most of the questions, if not all the questions from here on in this chapter, they're going to say something like this. X and Y are greater than or equal to 0. Or in the last question, they would have said P and Q are greater than or equal to 0. And what that means is you don't have to worry about them being negative. You don't have to worry about restrictions. You don't have to worry about absolute values because we've restricted the domain so it's only concerned with positive numbers. Isn't that lovely? And that'll pretty much be the way they're going to do them, I think. Alright, so last one here. There's an 8, and we want to break that down. 4 and 2, and then 2 and 2, and we're looking for a pair because it's a square root. So here's a pair. So that comes out, that 2, and there's already a 5 there, so you get 10. We also have an x. We have 3 of them, and we're looking for a pair of 2. We can definitely do that. So when x comes out, what's left inside is this 2 and also 1x. So that's what you get there. Next one, 75 is the same as 25 times 3, and then 5 and 5. Looking for a pair, there it is. We've got 3 y's, and so we can do the same sort of thing. Take a pair out, and we got 1 left over. So what does that mean we have? Well, we've got this 5 times that 4. So that gives us 20. And then we got this y coming out, and another y already there. Y times y is y squared. And what's left inside is this 3, and that last y there. Pretty complicated, isn't it? Okay, 27, 9 and 3, and then 3 and 3, so there's a pair. So we have 3 coming out, but we already had a 2 there. 3 times 2 is 6. We had 5 y's. So you can get a couple pairs there. 1 pair, second pair. So 1 y comes out, another y comes out, so that gives us y squared. And what's left inside is this 3 and 1 more y. Takeaway. 50 is the same as 5 and 10, which is 5 and 2. We've got a pair. So the 5 comes out. There's already 3 there, so 5 times 3 is 15. Can't take any x's out, but you already have 1 there. And what's left inside is the 2, and the x remains. Okay, we should have some like terms, I hope, or like radicals. 10x root 2x and 15x root 2x. So we got 10 of those, taking away 15 of those, so you're left with negative 5 of those. Like that. And then we've got 20y squared root 3y, take away 6y squared root 3y. So 20 of them, positive 20, take away 6, leaves us with positive 14y squared, square root of 3y. And that is our answer. By the way, I just want to make the point that 3q and times the 4th root of p cubed q and 3q squared times the 4th root of p cubed q are these like radicals. The way I defined it is they needed to have the same radicand, and these do, p cubed q, and the same index, 4 and 4. So are these like radicals? No, they're not, because also the coefficient has to have the same exponent and variables too. And although these have the same variable, q and q, they have different exponents. This one has a 2, and this one has a 1. So these are not like radicals. Okay, so watch out for that. You also have to make sure the coefficient out front of the radical is also the same, and I didn't talk about that when I defined it before. Okay, there you go.
Story.